In this video, I'm going to show you two examples of recursive solutions for binary trees. And each question is using recursive functions or methods in a different way. I'm going to start with the first one. Write a method that receives a binary tree and checks if it is balanced. So we're gonna implement a method called isBalanced, which returns a Boolean and receives the root of a binary tree. The root is of type binary node, which is a class like this, which is basically representing a single binary node. It has three instance fields. One is public element. The data type of E is going to be a generic type, so that you can replace E with any type you want, integer, doubles, string, whatever. And then the binary node points to two other binary nodes. One is called the left child, one is called the right child. And each of those left and right can have their own elements, left and right. And that's how you can create any binary tree with this class. The constructors are defined this way and this way. The first constructor creates a leaf because it sets the left and right child to null. That means it creates a node with no children. The second constructor allows you to initialize not only the element, but the left and the right instance fields in the following fashion. It has a toString method that prints the tree in the pre-order fashion, which means it first prints the root, then the left subtree, then the right subtree. I also have another toString method here that looks like this. It's a little bit more complicated, which uses breadth first search to traverse the nodes in a BFS fashion, which means top down, left to right. And this toString method will create a much more readable representation, easier to understand representation of a tree, which basically is a user-friendly fashion. It's a user-friendly way of printing a binary tree, the same way that we are used to draw binary trees by placing the root on the top and so on and so forth. There's one more thing I'm going to mention before I go back to the original problem, and that's the height method. I have defined a height method for the binary node, so I can use it in the balanced example. The height is defined recursively. If there is no left and right children, then the height would be 0, because if a tree has only one root, it has a height. Its height is 0 by definition. The definition is the length of path from root to the deepest leaf. When you have only one root, one node, which is the root, the deepest leaf would be the same as the root, and then the distance from every node to itself would be 0. So by definition, the height becomes 0. If the left has no children, if the left is null, then the height of the tree would be 1 more than the height of the right subtree. And if the right is null, then the height of the tree would be the 1 plus the height of the left subtree. And if neither the left nor the right are null, which means you have one left subtree and one right subtree, then you need to get the height of both of them, find the maximum of the two, and then add 1 to it. Why do we need to call the max? Because height cares about the deepest leaf, and the deepest leaf is in a subtree with the longest height. So that's why we need to get the maximum of the two, and whatever the max is, we need to add it by 1 to find the height of the original tree. So that's the definition of height in a recursive fashion. Now let's go back to the original problem. How do we solve the isBalanced method? Or how do we implement it? The definition of isBalanced is this. A tree is balanced if for every node in that tree that you pick, the difference between the height of the left and right subtree does not exceed 1, which means Either the left and right subtree have the same height, or they are different with only one unit. The height cannot be different more than 1 unit, like 2 units or more are not acceptable. If that's the case, then it's not balanced. How do you solve this? Again, recursive. Recursion would be the solution to many tree problems. If the root is null, they return true, because if you have an empty tree, we can assume that it's balanced. You cannot define it, but just let's define an empty tree as a balanced tree. That's an extreme case. We call it a base case because we are talking about recursive solutions. The second base case would be if the root is made of only one child, or if the root has only one child, which is the right child. Or I should say it differently, if the root left is null, right? If that's the case, then the right child should also be null. That means if it has no left child, you should have no right child. Or if it has a right child, the height of the right child should be 0, which means you should only have one child on the right and nothing else. If the right child has a height more than 0, like 1 or more, then it would create an unbalance in the left and right side. Similar story happens if the right is null. If the right is null, then of course left cannot be null because we already have passed this line 8. So if you are in this step, that means left is not null. So if the right is null but left is not null, then the height of the left subtree should be 0 exactly. If it's more than 0, then we create an unbalance, and that would not be a balanced tree. If none of these base cases are true, we have 3 base cases, that means you have a non-null root with a non-null left and non-null right child. So that means you have a root, you have a left child, you have a right child. Then you need to get to this trio of conditions. You have 3 different conditions, all of them should be true. If one of them is wrong, then one of them is false, then we have to return false. The first thing is the height of the left subtree and the height of the right subtree shouldn't be different with more than 1 unit. That means if you find the difference of the root left height and root right height and get the absolute value of that difference, this must be either 0 or 1. If it's 2 or more, we cannot have a balanced tree. That's one of the 3 conditions. What are the other 2 conditions? We need to have the balanced relationship in the lower levels. Not only the top levels should be balanced, but in the lower levels, we should have the same property, which means for every node that you pick, the left and right children should have the height difference of 1 or 0. So you need to call the is balanced again recursively for root of left and for root of right. If both of them return true, then we're gonna return true. If one of them return false, we're gonna return false as well. So there should be an AND statement and the operation between these. That's how the is balanced method looks like. And I'll later show you a quick demo of how to call this to check if it's if a binary tree is balanced or not. The next question that I don't want to solve completely, I just want to show you the idea, but I'm not going to complete it. I'm going to leave it for you to solve it, is called is symmetric. You're asked to write a method that receives a binary tree and check if it is symmetric. Let me tell you what symmetric is by showing you this example that I already have. I have a main method to test my solutions, and it has defined the binary tree like this. This is a binary node root. The root is going to hold the value 1. The children would hold values equal to 2. The left child is going to have these 2 subtrees, and the right child is going to have these 2 subtrees. And if I run it, we're going to print the root and root dot to string 2, and that's going to help us visualize the tree. This is the visual representation of the tree. This is the pre-order traversal of the tree. This is the breadth first search traversal of the tree. That's the easier to read representation. The root is 1. The left and right children are both 2. And then the left side, which is, let me see if I can select only the left side. Yeah, so this side is the mirror of this side. What do you mean by mirror? If I give you some annotation, it's easier to show it. So these are the leaves, I'm sorry, the edges. Let me draw the edges first to make sure you all see this tree. Now, let's talk about what mirror means. Mirror means this is equal to this. So these should be equal. Then it means the left child of the left subtree should be equal to the right child of the left subtree. So these two should be equal. Also, it shows that this should be equal to this, right? So when we say mirror, I mean, we mean basically if there's a mirror on the middle, the left side is the image of the right side in the mirror, right? And then finally, the 6 here is equal to the 6 here. 5 has no children on the left side. 5 has no children on the right side. 3 has no left child on the left side. 3 has no right child on the right side. So these nulls, the right child of 3 would be null on both sides. On right side and on left side, the left child of 3 would be null. So these two are also equal. So the nulls are, even the nulls are equal, right? So that should be a symmetric binary tree. So we want to create a method that shows whether or not a binary tree is symmetric. How do we do this? Again, we're going to use recursion. Let me tell you the idea. If you want to pause the video and think about it yourself, do it. But I'm just going to show you my idea. First of all, I would take care of an extreme case. If the root is null, then by definition of this is symmetric. I assume that an empty tree is symmetric because it has no like violation of symmetry. So it is symmetric. If that's not the case, then we're gonna call the isMirror, which is a method that gets 2 parameters, root.left, root.right, and checks whether the left subtree is the mirror of the right subtree. All right. This method is a helper method, and it's a recursive method. It is very common that when you're solving a problem recursively, you define some helper method. Why the helper methods are so commonly used in the recursive solutions? Because a recursive method must carry the important information in its input parameters. And the original signature of the method is symmetric, has only one parameter. But the isMirror, which is the helper method, must have 2 separate parameters. One is the left, one is the right. So this way we can compare the two as 2 separate parameters. So it is very common that when you're solving a problem recursively, you decide to create a helper method. The helper method is usually a private recursive method, but the original method might not be recursive. In this case, symmetric is not recursive by definition, but isMirror, which is a helper method, is recursive. And I'm going to call this private, make this private because no one's going to call isMirror directly. Now, you may say, can I just implement this symmetric in a recursive fashion without calling, without creating a helper method? The answer is maybe you can, yeah, but this is much easier to do, right? What I'm showing you is much easier to do. So let's look at the isMirror definition and see how we can solve this isMirror operation recursively. Basically, isMirror is going to get 2 trees or 2 roots from 2 separate trees and it's going to check whether one is the mirror of the other. We know what that means. We already saw an example. So let's see if we can solve that. We call the two input parameters first and second. We're gonna make sure that if the first is null or if the second is null, that means if one of them is null, the other one must be null. So if first is null or second is null, then first must be equal to second. Because if one of them is empty, the other one must be empty. So that's the base case of any of the recursion. Every recursion must have a base case. Otherwise, you're gonna have basically the stack overflow because the method is called recursively infinite number of times, and it's gonna overflow the program stack. If that's not the case, if the base case is not true, then you gotta basically take care of the recursive step. I leave this empty because I want you to think about it. I have solved the similar recursive problem for is balanced example, but now just use the similar idea. Just remember, you must call is mirror. And just to give you a little bit more help, you need to call the is mirror twice. Imagine you're calling the is mirror for this tree, right? You need to the first call would be a call that passes this node and this node. Then this first call will call the is mirror twice more. One should call it for this node and this node to make sure this node's subtree is a mirror of this node subtree. And the second time, it should call it for this node and this node. So we need to make sure that this tree is a mirror of this tree. Or this subtree rooted at 5 is mirror of this subtree rooted at 5, right? And I don't want to continue. Work on it, get rid of this line, and think about how to fill this recursive step. And after you do that, call this mirror for this example and see if it works or not.